Hello, everyone. Welcome to Nanoscience Engineering. This is Khalid Tantawi. This is lesson one, Introduction to Nanosciences. So first, let's talk about the definition of nanosciences. So, so nanoscience and nanotechnology, basically science, engineering, and technology conducted at the nanoscale. The generally accepted definition of the nanoscale is the range that goes from 1 nanometer to 100 nanometer. It can go above, a little above, like say 200 or even more. It can be considered in the nanoscale, but generally, most commonly, the range is going to be between 1 and 100 nanometers. At the nanoscale, atomic and molecular interactions cause the properties to be much different than at the macro scale. We're going to touch on this today. So let's answer this question. How many nanometers are there in 1 inch? So as we know, 1 inch is 25.4 millimeters, and each millimeter contains 1 million nanometers. So that means you have 25.4 million nanometers in 1 inch. Quantum versus continuum. At the nanoscale, behavior of materials is described using quantum physics principles, while at the macro scale, in the bulk of the material, and the micro scale, of course, behavior of materials is described using classical physics principles. The quantum affects the change in the physical properties of materials as a result of the small dimensions, like, for example, the melting point. Melting point of colloidal silver, for example, is different than for bulk silver. Continuous or bulk properties refer to the physical properties of the macroscopic material. So when you say bulk, the word bulk, basically, that means we're talking about the macroscopic material itself. Let's look at the categories of nanomaterials. In the first category, you have all 3 dimensions are in the nanoscale. In other words, all 3 dimensions are less than 100 nanometers. One example of these, for example, are the quantum dots. Quantum dots, colloidal particles. These have all 3 dimensions in the in the nanoscale. A good application, for example, is the QLED TV, for instance. The second category is when you have 2 dimensions that are less than 100 nanometers. In other words, you have 2 dimensions in the nanoscale and 1 dimension not. A good example of that are nanotubes and nanowires. As you see here, for example, carbon nanotubes. They have an application, for example, they have been used for the body of aircraft. In the third category, only 1 dimension is in the nanoscale, and 2 dimensions are not. A good example of this is the lipid bilayer membrane. The lipid bilayer membrane, for example, exists. For instance, it's the membrane that encapsulates the cell, the human cell, for example, is called the lipid bilayer membrane. In the in the membrane, only 1 dimension is in the nanoscale. Let's see how small is nano. So a water molecule, for example, is less than 1 nanometer in diameter. So it's a small molecule, but some molecules are bigger, a lot bigger. For example, polymers can be in the tens of nanometers. For instance, glucose is in the range of few nanometers, but proteins can be in the range of tens of nanometers. If you go up to the range of 100 nanometers, you will hit viruses. If you go up to the micro scale, to the micrometer scale, we're going to see bacteria and human cells. Human hair, for example, the diameter of human hair, for instance, is in the range of about 80 to 140 micrometers. The tip of a pencil is about 1 millimeter, and then you can go up and you can see objects that are bigger in everyday life. Elements in nanomaterials. So some of the most commonly used elements, for example, is silver. Silver is very commonly used, followed by carbon and by silicon and then titanium and gold. So these are very commonly used elements in nanomaterials. Potential risks of nanomaterials. Some of the potential risks include, for instance, cancer treatment with gold nanoparticles. This was actually a very popular research that came out 12 years ago, in which gold nanoparticles were used for treatment of cancer, in which the gold nanoparticle sticks to the cancer cell, and then by heating for example, using microwave, for instance, you can damage the cancer cell. Using TiO2 nanoparticles in sunscreen could negatively affect health if absorbed through the skin. The same thing for the gold nanoparticles. We don't know if there's any potential risk of using them. Quantum dots in LED TVs, QLEDs, can be toxic to the environment after disposal of the TV. Nanoparticles in boat and sea vessels coating can be toxic to the oceans. Antibacterial socks that contain silver nanoparticles can potentially be harmful to the person if absorbed, or not only to the person, but also to the environment. Fundamentals of nanoscience. So a good question that we should look at is why physical properties change at the nanoscale. When you have a bulk material that goes to the nanoscale, its properties change. Like, for example, the melting point, like we just mentioned. Let's see why. The first thing I need to know is that at the interface, sorry, at the interface between the material itself and the surrounding environment, there can be a layer that is different than the bulk of the material itself. Now, if you go down, the surface area of the material becomes bigger compared to its volume. So in bulk materials, the physical properties are determined as the average of the atoms or molecules that make up the medium. Therefore, you apply Newton's mechanics, Newton's principles. In the nanoscale, the rules of quantum mechanics are applied. The physical properties can be different. Nanomaterials have very high surface energies due to the extreme surface area to volume ratios. This is a very important term that we're gonna hit on and in detail, because it is actually one of the major reasons for the differences that you're gonna see in the nano scale compared to the macro scale. To reduce surface energy, nanomaterials tend to agglomerate. So this is one of the, self-assembly of nanomaterials is spontaneous. It's typically spontaneous because they tend to reduce the surface energy as possible. There's a lot of exposure to the outside environment, so they tend to reduce that by aggregating. Example, when determining the boiling point of 1 mole of water, it is the average of the behavior of 6.022, of course, it's Avogadro's number, times 10 to the power 23 molecules, of which most of them are in the bulk of the water, and only a minority of them is exposed to the outside environment. Example 2. Gold, for example, is golden in color, the bulk gold, but in the macro, of course, in the micro scale. But if you go to the nanoscale, like for example, colloidal gold particles, the color changes to red. The same thing for colloidal silver. The colloidal silver, depending on of course the particle size, is yellow, but the bulk silver is silver in color. So this is one of the major things that a very important term that needs to be understood in the nano world: the surface area to volume ratio. The main characteristic feature of nanomaterials is the extreme surface area to volume ratio. I'm going to show you an example in a minute, but let's see more details about this. Surface area to volume ratio is extremely high for nanomaterials. The chemical group of the material at the interface surface between the material and the surrounding environment determine its chemical and electrical properties, as we know. So like we saw the example, the melting point for colloidal silver, for example, is lower than that of the bulk silver. And of course, the reason for that is because there's the surface area of colloidal silver is very, very high compared to its volume. So most of the silver particles exposed to the outside environment. In other words, it requires less heat energy to remove the atoms and therefore melt. Let's look at this example here. A gold cube with a side length of 1 meter. So we have a very large cube of gold of 1 meter. So it's 1 by 1 by 1. Was cut into pieces with a side length of 0.1 meters. Then they were cut into pieces of 0.01 meters. That is 1 centimeter. Then into pieces with a side length of 1 millimeter, 0.001 meter. Then into pieces of length of 1 nanometer. Let's fill out the table over here. So this is a side length, as you see. And we go from 1 meter all the way to 1 nanometer. The volume of each cube that we get, the surface area of each cube over here, the surface area to volume ratio of each cube, the number of pieces in total that we have, and finally the total surface area that is achieved, the total surface area. So as you see here, when you have one huge piece of gold, the surface area is 6 meters squared. Why? Because you have 6 faces on the cube, right? And we have each side is 1 by 1. If you cut it into pieces of 10 centimeters, the side length of each cube, you end up with a surface area, total surface area of 60 meters squared, a lot bigger. If you keep cutting it into 1 centimeter, then all the way to 1 nanometer, as you see, the total surface area becomes 6 billion. So we start at 6 meters squared. Now we have 6 billion meters squared. So as you see here, the cubes are now the small cubes that have 1 by 1 nanometer. The surface area to volume ratio is 6 times 10 to the power 9. As you see here, it's significant. It's extreme. So as you see, we started with 6, but here we have 6 times 10 to the power 9. So in other words, 6 billion surface meters to the power -1 is the surface area to volume ratio compared to 6. As you see, that's why this here will have much different physical properties than this part over here. Because here we have the surface area, it's exposed, almost everything's exposed to the outside environment. So it's gonna have different melting point, it can have different color, interaction with light, and so on. Effect of the shape on the surface area. Now, if we have different shapes, the surface area is gonna be different. Take this example here, for instance. All these, as you see, all these shapes have the same volume. They will have the same volume. But if you take the surface area of each, the cylinder, the cube, and the sphere, you will find that the surface area of the sphere is the smallest. And this is a very important thing. So the smallest surface area to volume ratio is achieved when you have a sphere, a spherical shape. Let's look at some applications in nature for that. So this exercise question, you know the Smurfs, maybe the Smurfs is a popular cartoon that came in the 20th century. And it's basically about humanoids. Let's say they're the size of a mushroom size. So we're talking about like few centimeters. And The question now is, do you think it's possible to have humanoids that small and walk in the wild scientifically? So as you see, the human shape basically is not made to reduce heat dissipation. So as you see here, the surface area is very high. The surface area to volume ratio becomes extremely high as the dimensions become smaller. So in other words, if you have humanoids that small, they would need a lot of time. They would need to spend a lot of time just eating to compensate for the heat loss from their bodies, or otherwise they're going to freeze to death. Now, that's for the same reasoning. The small warm-blooded animals, as you see, like for example, mice, rabbits, or any other animals, you'll see them that they are spherical in shape. They are spherical in shape. Why? Because this is how they reduce heat loss as possible. Otherwise, even then, they still need to eat. They spend a lot of their time just eating to compensate for the heat loss. And the spherical shape actually reduces the heat loss as possible. Effective size changes on forces. So we're going to discuss this in the next lesson. And as we saw, as the volume of objects decreases, then the surface area to volume ratios increases significantly. Therefore, there's going to be faster heat dissipation, faster evaporation, more energy required to compensate for heat loss. Let's look at some nature-made nanomaterials. Bone tissue, for example, the bones, these are nanocomposite materials. So just to make sure you understand what's a composite. A composite basically is a material in which you have two components. You have two materials that are not mixed. They are not mixed, but they function together. One of the two is called the matrix material, and then you have the filler or the reinforcement material. So you have the matrix and the reinforcement material. A good example of composites is, for example, concrete, reinforced concrete. So, for example, concrete, when you have the steel reinforcements, you have a composite material. But of course, concrete is not a nanomaterial. Okay, because the interaction is not done at the nano scale, at the nano level. So bones are composites in which the matrix material is soft and organic. This is the collagen fibrils, reinforced with inorganic crystals of calcium phosphate or hydroxyapatite. So this, of course, this interaction is done at the nano level, and therefore it is a nano material. Another nanomaterial is blood, for example. Blood basically is you have colloids in blood. In other words, you have nanoparticles that are dispersed in the fluid medium, but they are not mixed. Okay. A third example is spider silk. So spider silk, by the way, is the strongest. It has the highest tensile strength of all known materials. The interaction is at the nanoscale level. Proteins are organized on the nanoscale level. So these are some examples of natural nanomaterials. So as you see here, the main feature for nanomaterials is that the organization, the interaction of the materials happens at the nanoscale level. Thank you for attending lesson 1. Please go to lesson 2. Thank you.